right, so we're back for another episode of Going Native. I know it's been a while. I'm sorry that we missed February. But then again, we gave you 2 hours or 3 hours of Herb Sutter, as well as some other very meaty, excellent C++ content, so don't be too upset, man. Anyway, I'm joined today by Eric Battaglia. How are you doing?
Doing great.
Excellent. So just to refresh people's memory, you are?
I'm a program manager with a Visual C++ team. I work with communities.
Excellent, man. Now, real quickly, you started a really interesting blog post called Jumping into C++. Tell us about that.
So I used to be a C developer and did a bunch of middleware and .NET managed stuff, and I decided I would get back into C++. So this is a series of posts that illustrate me jumping in via some simple projects, and I get feedback from the experts here at Microsoft and out in the community. It's been interesting getting instructed by the community about all the different ways that I can improve my code.
Yes.
So, yeah, it's great stuff, though. Yeah, it's really for those of you who are watching this that are thinking about C++, it certainly is a great way to get back into the language or get into the language and then learn the best practices. Right? Don't be afraid to share any of the code you're writing.
Excellent, and be prepared to have your stuff optimized for you.
Yes.
And that's okay, man.
Yes, you can go from reading a simple file to having a memory-mapped, multi-threaded reading from a file, and that's what happened in one of the posts. So it's great stuff, though. It's nice to see that everybody's so technical, and you'll learn more about everything than you thought that you could.
Cool, man.
Yeah.
So as we move along here, I mean, I know that there's a C++ and Beyond was announced that's going to happen in September. That's rock and roll, so people, you definitely want to look out for that and try to get yourself some tickets. You always want to go see those guys speak. The other thing that I wanted to say is we introduced people on Channel 9 to ImageWatch, which is a Visual Studio plugin for C++ developers to be able to basically step into pixels, step into the image at any point during the image processing point where you set a debug. So it's actually a really, really useful visualization tool for those of you that do hardcore image processing, video, still photos, whatever. What we're gonna do this week for this show is kind of dig a little deeper with those guys. We're gonna meet another developer on the team, actually a scientist dev. They're both really hardcore C++ guys, and in some cases we'll even program down at the SIMD level for those tight inner loops to optimize. So we're gonna go talk to him, man.
Excellent. Yeah,
enough blah blah blah. All right.
Yes, let's go.
All right. So we're gonna dig in today into ImageWatch. Let's meet some of the people here.
Hi, I'm Wolf Kienze. I was here 2 days ago to introduce our new ImageWatch tool.
You were.
And I'm happy to be back.
Excellent.
And I am Matt Utendale, also from Microsoft Research.
Awesome. Now, one of the things that Niners have been asking for in our show, Going Native, is, hey, how do people at Microsoft actually use C++ to build interesting things? Well, we are introduced to the great stuff you guys did in ImageWatch. So today we kind of want to dig into how ImageWatch works and how you guys implemented it using C++. Why you use C++ is probably pretty easy. We don't have to spend much time on that, but let's start there.
So maybe we can take a step back and talk about why we even built ImageWatch.
Sure.
Right, because we built a lot of applications that process images and photos. Right, so a couple of things that we've released are the panoramic stitching feature that's built into Windows Live Photo Gallery.
Okay.
We worked on PhotoSynth for the Windows Phone.
Awesome.
We worked on a feature called PhotoFuse in Photo Gallery. We have a new desktop app called Cliplets for generating short form video. So we've, over the years, been working in this space, and just debugging these applications was a lot of effort, right? Like how do you debug? How do you watch like your algorithm take shape? How do you step through your code and see what's happening deep down inside the algorithm? And for a long time, we were using what would I call like printf style debugging, where you just dump it to disk, use some other image editing application to open it up and take a look at the bits. But that round trip is a real pain. So Wolf joined the group, and he's like, well, I've got a much better way of doing this, and he just built this ImageWatch feature into Visual Studio, which has been just a huge boon for the productivity of developers in our group.
So that's how it worked. Wolf came in and said, hey, I got a better way of doing this, and you just did it?
In a way, yeah. Well, I'm sort of like a sort of a low-level programming and debugging sort of fan myself, and so I was just curious how that would work. And actually, we had another incarnation of this before, which was a standalone viewer tool that would basically talk to the app as it's running. It's kind of like one of these spy tools. I don't know if you remember those, where you can spy on Windows handles and stuff. And so we basically built this first, so you could spy on images in your apps. And then like only after a while, I discovered, hey, there's like this amazing extensibility framework for Visual Studio, and so basically then we just took the code and kind of put it into Visual Studio, and now it's a plugin.
Excellent.
Yeah.
So let us dig into this. Okay, I see C++ on the screen. Everybody's excited. Eric's dancing over here. So can we talk a little bit about how this thing is built?
Sure. I mean, we could. So I'll introduce the program that's here on the screen.
Perfect.
This is sort of one of these classic image processing things. There's a paper called multi-resolution splines for making an apple and orange sort of fused together, right? So here we have a program that loads up an apple and an orange, and then an algorithm that processes those two things to make them seam together, right?
Excellent.
So this is also a step that's inside of our panoramic stitching application. When you seam two images together in Photo Gallery, how do you make it look like that seam disappears, right? So this is just a toy example that is a nice demonstration of that. So we have Image Watch, which Wolf presented a couple days ago on Channel 9, in the inner loop here, watching this processing happen. So we're here at a breakpoint, and I'm just iterating through different blending strengths, right, on this image. So here, this is essentially no blending, and if I step forward to the next step, you can start to see it taking form. There's a little more and more blending, right? And this is all happening live, right? I'm looking at these images take shape right inside the program, right? So that's what
Nice.
Image Watch enables us to do. Yeah.
Really, really cool.
Yeah.
Again, for the people who didn't see Wolf's thing, obviously we set a breakpoint in code. We get to see what the image looks like at that exact moment in time versus in a watch window, which is very convenient. So just to catch people up to speed, everyone should watch that video. If it hasn't, 6 minutes long, get all the information you need. It's rock and roll.
Cool.
So, I guess really what I want to know, what we want to dig into here is, in some sense, how you built this. Now, I'm not necessarily talking about how you plugged into Visual Studio. To me, that's a side effect. You could plug into any number of things, but the core of your code is written in C++. Things like that I'm very curious about is like your use of templates. Like, you have an extensive use for genericity. Sorry, got gum in my mouth. Can you talk a little bit about your architecture, your design?
Yeah, I don't know, Matt. Should I?
Yeah, sorry. Take a stab at it.
Yeah. Okay. So basically, we have this library, the C++ library that we use for all the applications that we write, all the prototyping that we do at MSR, like those applications that Matt mentioned before, like the panorama stitchers and the Blink app and all those things, and and this is basically. Yeah, pure C++. It actually builds on GCC, which is something we're proud of.
Nice.
So, it's a library that has evolved for a couple years now. That's why you see these things that don't look exactly that modern, like classes starting with a capital C and stuff like that. But we have, for example, since you asked for templates, what we do for the image class, which is sort of the central data container. We have this is actually a class template in our case, and that's convenient because when you access pixels in an image, sometimes let's say you iterate over an image and you access every pixel and you change the color or something, then it's obviously more convenient to access something as let's say if you have an RGB pixel, like 3 channels, right? You have 3 values. If you access this as a struct, say, right? So the pixel type would be a template parameter this image template, and yeah. So for example, what you see here, that's the C RGBA image is actually a template that has a struct as a template parameter, which is an RGBA image. So you can access the R, the G, the B, and the A channel in that image. Yeah, that's one use. That's one place where we use templates.
Right. So yeah, I can. So I'll add a couple things. So I mean, C++ is what we do all of our core image processing in. You know, for some of the apps that we've released, like we did this recent one called Blink on the Windows Phone. There, the UI, the user interface layer is written in managed code.
Sure.
But all the image processing code is written in native. And one of the reasons we love native is we can use a lot of these modern features like autos and templates and threading and lambdas, but we can also go very low level. So if you look at the inner loops of our code, we're using what's called SSE intrinsics on the x86 or ARM Neon intrinsics on the ARM processor, and that's so that we can access those multimedia instructions that really make our code fly. Right, and that's one thing that we love about programming in C++ is that we can go, sort of high-level modern, but when we need to in the inner loops, we can go processor-specific, tweaky instructions that make the code go really fast.
Excellent. Now, can we talk? I mean, because we spend so much time really talking about the higher-level C++, if you will, right, where we talk about the new C++ language features, right. But we don't really spend any time talking about, number __ ASM. The ASM blocks.
Right.
So what is that, when you're saying in these inner loops, what does that code look like? Can we look at that?
Sure, we can bring some up. Let me stop debugging. Well, it's probably easier if I stop debugging here. So, ASM is not something that we use an awful lot of. It's more what's called the intrinsics, so _mm add 16 _ I forget what the equivalent neon ones are.
Okay.
Yeah.
But these are what's called SIMD instructions deep down that map to one-to-one. Looks like a C++ function call. Maps one-to-one to a processor instruction.
Excellent.
Right. It's an opcode in the processor that does 4 parallel additions. Right. For example, and that's how when you're processing images, there's a lot of parallelism there. Right. Available to. So you can do the Wolf mentioned RGB images, right? You can process red, green, blue in parallel through one of these SIMD instructions.
So one thing real quick, one of the features of Visual C++ 2012 is the backend compiler does what's called auto-vectorization, which in fact does exactly that if it's a vectorizable loop.
Yep.
So if your inner loop is vectorizable, and you probably don't have to use _mm anything, and let the compiler handle for Neon and Intel instruction x86 for you. You mentioned you're using GCC, but
yeah,
I just wanted to throw that out there just so that our audience understands that you can manually do this yourself, or
that's true.
If you're using Visual Studio, you can let the great work of unbelievably can't remember his name right now.
Jim Radigan.
Thank you. Jim Radigan's team of sharpshooters who build the back end.
Yeah.
I see it separated out into
Thanks, Eric.
Yes. Okay. So here I finally brought up some code.
Okay.
Yeah. So yeah, auto vectorization is definitely a feature we use in some places. When we're what's happened recently is we've had to run the same thing that we've always run on PCs, but on sort of lower powered machines, right? So we're now having to, people want to stitch their panorama on a phone, or people want to do it on the Surface, which is not as powerful a machine as a desktop PC. So we found that, in a lot of cases, really those core inner loops, you really want to hand tune them. So auto vectorization helps definitely in certain cases, but when we identify those sort of hot spots in our code, we have experts on the team that can go in and really refine those inner loops. But it's all C++ code, right? It's not ASM. It's not. So here's an example of a C++ loop that's EPU8. We're doing a blur across the image.
Okay.
So this is what it's not pretty code, but but we've got a great IDE that lets us debug this. It's all in line in our C++ code.
So you can set a breakpoint on anything there and debug into it.
That's right. Yeah, exactly.
Now, it kind of would be fun. I mean, to sort of put a debug breakpoint on something there, load up an image, see where we are. Anyway, you can do that with ImageWatch, folks.
Yeah.
Like that's how low you can go.
Yeah.
That's pretty killer.
Yeah. I wonder if we can find actually like a code path that we hit. Like
I don't think this particular code path is used in the example I was just showing, but we could with a little bit of effort we could probably
actually
get you there.
An easy way to get there. I'm not suggesting we do this now, but a cool way to get to a place like this is if in ImageWatch we have this. You can hover with your mouse over this view of the image, right? If you right-click, you can copy the address of that pixel that you're hovering over, and so you can then paste that into a memory breakpoint. And sometimes that's kind of fun to then just like run your program again, and then you basically always end up in some instruction that actually writes memory, which quite often is a vector instruction.
Cool.
So here's copy pixel address.
Yes.
And then you could set a breakpoint on that pixel address, and then we could probably get there, figure out who.
Yeah.
Awesome.
Yeah. What function created that pixel?
So now, in terms of, we could kind of shift focus a little bit, maybe talk a little bit about some of these image processing algorithms that you use. I mean, you guys are in MSR, Microsoft Research, Redmond. You hang around a lot of scientists. You're both probably got advanced degrees yourself. You're certainly great engineers. What's going on in the science of, high performance image processing? It has to evolve as well. Like, are you guys using very modern techniques, or? That's my question.
Modern techniques in terms of programming languages, or just in terms you want to hear about the state of the art of computer vision research? Exactly.
So in other words, because that must be so C++ is the implementation tool.
Right. So the space that I work most in is this evolving field called computational photography. So computational photography is, traditional photography, all of the sort of innovation maybe happened, in a fancier lens design, or better film, or a faster shutter, this very sort of mechanical stuff, right? But as computers become more and more powerful and we can inject processing into that pipeline, all of a sudden you can make different design trade-offs, right? You can use a cheaper lens because you can do computation behind the lens using a processor, right? So this is a sort of fast evolving field. I think we're about to go to the 4th annual International Conference on Computational Photography because it's so new. It's only 4 years old, right? And some of the people who formed the first conference are members of our group, right? So MSR is actively involved in this space. And really simple examples of computational photography are the panorama stitching. That's sort of version 1 of this. But you'll see fancier and fancier algorithms come out of the group that start to repair blurred images. If you're moving the camera, all of a sudden you can do some smart stuff. Some of this, implemented here in C++, but these smart codes that what's called deconvolve the image and fix up this blur.
Excellent.
Or you'll take a noisy image and remove the noise, or you'll take multiple images and combine those in interesting ways to get like a cool background motion blur effect while the foreground's sharper. So there's just a ton of ways in which computation is going to help photography, and that's something that we're I think at the forefront of, and you'll see a lot of cool apps come out on Windows Phone and on Surface that take advantage of this work that we're doing in MSR.
Absolutely. I mean, in some sense, the lens capability of the lens plug-in capability for Windows Phone is exactly computational photography. Right?
That's right. Yeah, exactly.
And your app, your Blink app that you showed us in Wolf's excellent demo is also computational photography, which is quite interesting. And let's talk about speed. You mentioned that you can get into tight inner loops and really kind of hand roll these instructions for any number of processors or architectures, ARM or x86. The question I would have is, how are you dealing with parallelism, right? Or concurrency, more accurately, right? So concurrent programming.
Yeah.
Take a stab at it?
Yeah. So I guess the way that we do it, which is I think a very common way, is to process the images sort of in tiles, right? So you basically, you divide images into tiles that are small enough so that they, are friendly to the cache, and then we have basically a framework where we define any operation on an image on a tile, and then sort of the framework takes care of the tiling, kind of like C++ AMP, I think, is often introduced, where they have this mechanism that you can have a tile of a certain size, and then you have sort of variables that are local to the tile, and so we kind of have this for the CPU, and sometimes it's a little tricky to write these tiled image processing functions, because let's say it's simple if you never actually look outside of your tile, but if you do, then it becomes tricky, because then the whole scheduling is affected, and then you have to sort of make sure you sort of read and write in the right places. And so we have basically the library that we're using has we sort of rolled our own multi-core framework for tiled image processing that we're using actually more and more now, that even phones have 2 cores or
Sure.
And
but that brings up a good point. This was actually mentioned on the Channel 9 thread by, Niners are relatively smart, right? Super
of course,
smart guys out there. Relatively, I was joking. So you're CPU bound. Now, why not target the GPU, which has sort of a nice...
Yeah. Matt, you want to comment?
Yeah, no, it's a great question. I mean, I think Wolf mentioned earlier that this library has evolved over 10 years.
Yes.
So we have code, right, that's 8 years old, that was written by an expert in image processing that we still want to leverage, but hasn't been reworked for the GPU, right? And once you start having, I'll list a variety of reasons. Once you start having this sort of some of your code running on CPU, some of your code on GPU, that transition between CPU GPU is expensive. So what we found is that for many of our applications, we're better off just staying on the CPU, and the CPU has some really good image processing functionality that we can leverage. But that being said, the GPU is really good at a lot of things. So in the Blink app, we're using both GPU and CPU. So Blink app, you'll see what it does is you take a burst of images, and this is sort of magic that happens behind the scene. I don't think even a lot of people notice this, but I think that's the great thing about the software, is that all the images then are stabilized for you, right? So as you scrub between them, it looks rock solid, like, wow, I really was holding my hand still, but that's not the case. The software stabilized it all for you, right? And so there, the trade-off, we did the analysis of the images on the CPU, right? Because we had these existing libraries that extract feature points and do all sorts of complex computer vision. But then the final rendering and the warping of the images that needs to be done in order to make it look stable, that's all GPU coding, and GPUs can do that in their sleep. They're great at that. So so we definitely do leverage the GPU in places, but these libraries that we have that we've built up over years are CPU libraries. There's a couple other sort of subtle things that have come up over the years, like on a lot of platforms, if your app is backgrounded, you don't have access to the GPU, so we always had to have a CPU fallback anyway. And that, we saw that on Photosynth, for example.
Sure, I mean, I guess that sort of makes sense why they would make those decisions in their design for backgrounding.
Right.
So for phones, for example, I mean, your stuff runs on phones, or just talked about the Blink app. You want to preserve battery, and so the only problem of being CPU bound, doing a lot of computation, is you're using a lot of electrons. And what we tell everybody, and sort of the mythology out there, is, oh, well, you can do the same type of computation on the GPU, which is just basically sitting there, right? It has all of these execution engines that are just raring to go. So you should use that and use less electrons and get the same work done. But this is sort of part of the mythology of general purpose programming on the GPU, because it really isn't all that general purpose. You have to really have a problem that will fit into the mold of the GPU. But it would be interesting to see if some of the algorithms you guys have developed could run as a kernel inside of AMP.
Yep.
Right.
Yeah, they definitely can. I mean,
Yeah.
a lot of what we do is suitable for GPU.
Cool. So I just managed to piss off the C++ AMP team. So Eric will have to clean that up for me later.
I think this brings up a larger question. You've got an older code base. I think that there are a lot of people out there doing C++ that are maintaining older code bases. What do you see as a tension between using more modern C++, balanced against maintaining and not wanting to mess with code that's 8 years old that you think is probably fine and you might introduce risk if you were to bring it forward?
Yeah, no, it's a great question. I mean, I was talking to Charles earlier in the show about, or before the show about, porting a lot of our stuff to WinRT, and we had done a lot of sort of the things that WinRT really does a great job enforcing, like, all operations are asynchronous, and they provide a great multi-threading framework or multi-core framework that we had sort of rolled our own. So there's a little bit of, moving into the modern world, but there was a little bit of attacks there. But I think we're gonna see benefits from doing that. But I agree. I mean, we've had sort of expert researchers come through the group that have just built great technology for us in these existing libraries, and by staying on C++, we've been able to move those forward. And some of these things we're just not really realistically gonna touch.
Sure.
Yeah.
I mean, and that seems to be the case. I mean, it brings up a great point that Eric has raised here in terms of, because we have been talking about modern C++ now for the past 2 years. I mean, Microsoft shipped Lambdas, I guess, 4 years ago now, maybe longer. Right. But there's always a conversation about what modern actually means. Does it mean C++ 11 specifically? That's debatable. There's certain patterns that you use. So in this case, where you guys are all about perf, and as you said earlier, you're using C++ at the lowest level that you possibly can. The question that kept kind of ringing through my mind this whole time is, why are you using classes at all? Why don't you just use C? So I mean, I'm not trying to be, I'm just curious, when you have this type of algorithmic design and implementation, how is the C++ model helping you? So, and that's actually going to be useful for.
I mean, I could talk first, and then let you. So I mean, if we break open this new app that we're developing for Surface called Cliplets, it's littered with STL, smart pointer, unique pointer, shared pointer, unique pointer. So we love STL for memory management, for just being very good about resource management and RAII patterns. And so that's all over our code. So at the level outside the inner loops, we're using a lot of these modern C++ features that we like, that are a huge benefit to our programming. So I showed you some inner loops, but I didn't show you sort of the outer part of the code, which is using vectors and algorithm and unique pointer everywhere. So.
Cool.
Yeah, I think it's actually interesting. I was just thinking what kind of C++ features we're using, and I think since this thing has been growing for like 10 years, you can almost see there's certain areas in the code where like certain things were, I don't know, new or hip in C++. So there's like parts where there's a lot of templates, and then there's parts where there's interfaces that start with a capital I and double pointers, and it almost looks like COM, and then there's and then there's a inline assembler, and so it's I think it's just a good example of a code base that has been growing for a long time. And I would say nowadays, if you look at a program like this on the outside, I mean, you're right, we're not. So we have this image class that we're using, and then we have algorithms which are pretty much all like static functions, like free functions, and that operate on them. And and then under the hood, there are some things that are that have class hierarchies and have virtual functions and stuff like that. For example, the multi-core framework that we have, where we processed an image in tiles. So the function that processes the tile is actually like a derived class of some sort of transform interface, and then you have a virtual function that you call to actually access the, the process the pics and stuff like that. So there's a little bit of everything, I would say,
Great.
depending on when it was written and what it does.
No, and I wasn't trying to be facetious. I mean, the key is it's always nice to be able to structure your code, and that's object orientation, and then generics, templates, right? It's great to be able to write generic classes and stuff. I mean, that's what you guys have already talked about. It's very powerful. Adds to compile time burden overhead, but. I just kind of, it's important that we have this conversation because we always sort of fluff everything over and don't, let's talk about some of the challenges. I mean, Eric, again, that was a great question because what are some of the challenges of taking an old code base, the legacy that you can't necessarily get away from, and you probably don't want to, but let's say you do want to get on this modernized kick, let's modernize everything. That's going to be challenging, right? We don't necessarily suggest people should do that just because they can.
Yeah. I think something maybe a related point is that we were actually I mean, this has actually changed recently quite a bit where, the phone and Windows and it's all basically modern C++. So it's all like, latest compiler but some groups that we worked with in the past, they basically had either like an older version of the compiler or they said, like, no, we don't do exceptions, or they said something. And so it's almost like we had to have a library that is at the sort of, how do you say, like the common denominator of what sort of all the coding styles in C++ that are there in the company. And and so that's until very recently that's what we've been doing. And now since we're in RT, we're actually think, there's all these cool things that we can have like on the outside of our library that we can do.
Sure.
And that's what we're doing.
Yeah. No, I mean, it's great to see the company moving forward and embracing a lot of these modern C++ things, because I think, we've been fans of sort of these more modern techniques for a long time, like even to the point of using exceptions. But because we work with so many different groups around the company, we had, like Wolf said, program to the least common denominator, and it's nice to see that moving up now, so we can take advantage a lot more.
Interesting. Yeah. And exceptions is a sort of a can of worms, but I think there's legitimate arguments on both sides, and we still have the argument raging inside of Microsoft and other companies that have large numbers of people writing native code. Like all of our products are written in C and C++. But, does it really matter for an application like this if you use exceptions or not? Can you explain like what some of the pitfalls could be, or what some of the challenges were when you made the decision to use exceptions?
So the core library does not use exceptions.
Why?
Why? Oh, because we had a couple of customers in the company that said, like, we can't ship your stuff if you throw exceptions. And we are we are developers we are in Microsoft Research, but we are developers, and we sort of like to consider ourselves sort of like a product team almost, and we like to ship our stuff and make it production quality, and so that's why we just have to play by their rules. But of course, in the apps that we write, especially once you get to like .NET land or something where you have exceptions there, it's
understood.
Yeah, no, it's a really interesting debate, the exception versus error code debate. Because I find that especially in image processing apps, we tax the memory. Right, so out of memory is sort of a theoretical thing for a lot of apps, but out of memory really happens in our apps. If you and we don't necessarily want to take down the whole app. We don't want to crash the app and you can't save the project that you were working on because we run out of memory. So it's just a question of sort of learning one error propagation pattern versus another, and we really do, like, this code is actually pretty robust to out of memory and all these things that happen in the real world. You'll see like our Microsoft ICE panorama stitcher, which can create a 10 gigapixel image. Sometimes out in the real world, somebody runs it on a underpowered machine and it runs out of memory, and we get but it doesn't take down the app. So.
Sure.
But what's interesting about that is, based on if an operation fails, the caller has to take some sort of action on it. So if an image process fails, it's not clear to me what the correction would be anyway, right? So that's the other side, is if you're going to throw something that's exceptional, are you going to be able to react on it at all? And it doesn't matter if you're using exceptions or return values. I'll bet a lot of applications throw out a lot of those return values anyway, because they don't really, I mean, what's the recovery look like? And I would imagine a lot of these, if I called into image and said, hey, go do this transform, and said false, what am I going to do? Is the image bad? Is a hard drive on fire? Is it, right? You know, as long as you don't pull down other apps, which is probably handled by the library, I would assume calling in the library that it's not going to kind of do horrible things to the environment. And then when it comes back to me, it's kind of up to me to say. So,
you know, I mean, it's like a lot of, you know, a lot of the design decisions in this library were based on this Microsoft ICE app that we did 5-6 years ago. And it's Microsoft ICE you can take 1,000 images and stitch them together into one mega image, right? And just the coding discipline in making sure that we respected sort of the memory limits of the machine that we developed there has really gone forward, taken us forward in lots of. It's been really beneficial, I guess, you know, because on Windows Phone there's not a lot of memory on that machine, so a lot of this discipline that we developed in developing this panoramic stitching application that has to handle massive data sets has moved forward nicely. And it's, you know, we do handle things like ICE runs out of memory, or it uses the available memory in the machine, but then sometimes it has to back to disk. You know, our framework lets it virtualizes these images and lets it back to disk. And there are things that really happen, like, oh, well, the temp disk that you pointed ICE at is out of space. User go plug in another temp disk. So we handle that exceptional situation, and we let the user go in and plug another disk and then say start over. So there are cases where you can restart from exceptional situations that yeah.
So as we wind down here. What's the gnarliest algorithm you guys had to implement here? Like, when you think through because you guys are doing incredible computation here. What's the gnarliest? Use surfer terminology.
Maybe we should each answer.
Go ahead and each answer. Each answer if you want.
I would have to think about it. I don't even know.
Okay. I mean, I think the work you did on you know,
the object detection
stuff recently is pretty gnarly.
Yeah, that's true. Yeah, so there's one. Yeah, this is one thing that it becomes more like a standard thing nowadays, which is object detection. So that's something like, you know, the face detection on your camera, or, you know, you could detect other things like your pet, or or like a person on the street, or something like that. And so these algorithms are pretty mature now, but they have this this problem, I would say, that they are a little different from these the classic image processing applications, which are inherently sort of SIMD parallel. And so these are a little harder to get right. I mean, there's a whole, you know, scene that does this on the GPU, and then there's people who don't do it on the GPU, but they're not, you know, you deal with sort of pretty random memory accesses in your image, and when you build object detectors and recognizers. And so, yeah, this is something where that I worked on quite a bit lately, and that was tricky, I would say. Yeah.
So the question I want to ask is, if say we've got someone who's experienced C++ and not experienced. We'll start with the not experienced. Do you recommend they look at is the ImageWatch source code available, number one, and is that where you recommend someone looking to see the modern style and maybe doesn't want to have their hair parted by going and looking at, or seeing more complex kind of library functions? I don't even know if those are available, but is this, so, we've talked about a lot of complex algorithms and processing and assembler and those types of things, but maybe a lot of C++ developers that are new might not need to do that.
Yeah.
So I'm wondering what would you say to them? And then the ones that really like eating the technical stuff, like, well, I guess they'll go out there and do it anyway. So what would you say? I mean, was it, what would you recommend they go look at? Do you have a tip for those types of folks?
You mean
the newbie C++?
Okay, so not specific to not specific image processing, but just
just as a C++ developers. You guys are C++ developers. What would you say to those guys and gals?
I'm not sure. I mean, I don't know if this. I haven't actually looked at it, but I heard that Bjorn Stroustrup wrote this is it a book or an article basically meant for first-time C++ programmers?
Yes, you did.
With modern C++ that I don't know if this is out. Probably, do you know about it?
Well, he wrote a book called Introduction to Programming, where it's first principles, and everything's done in C++.
Yeah.
He hasn't made that C++ 11y yet.
Oh,
It's
I
something
see.
he's working on his next book, which is going to be all C++ 11, the new language.
Okay, so then that isn't an option yet. But this is sort of the first thing that popped into my mind. Yeah, for a newbie programmer. But I mean, just like let's say the code that, for example, the source code that we have here that's behind ImageWatch. I guess that's more an example of how to, you know. It's almost like a more real-world example, I would say, because it uses like a lot of code from a lot of different sources and different times in C++ history, and so I think it's also a very good example. It's just not a good introductory example.
So yeah, you know, in general, it's harder for me to speak to the question in general. Like in the space that we work in, there's for developers outside of Microsoft, there's this OpenCV library, which uses a lot of modern features. You know, has very similar templated image types, and we designed ImageWatch, you know, to work well with our internal libraries, but we also designed it to work well with this OpenCV library that's available outside of Microsoft. So anybody who's interested in this space, I would encourage you to, you know, download OpenCV and watch the Channel 9 video from a couple days ago where we had a nice OpenCV example of stepping through these these image processing applications. And that, you know, OpenCV, you don't have to necessarily be familiar with the implementation of all these details. If you want to blur an image, it's pretty trivial. You know, CV open image into a CV matrix and CV blur image, and you're done, right? So so certainly people interested in this space, I would recommend playing with OpenCV and playing with ImageWatch to see how it works. It's a great, I think ImageWatch is actually a great learning tool for. You know.
And in OpenCV, you could dig in and see the source code for the blurring operation itself.
If you really, if you want to dive down, you can do that too, right?
Excuse me. Yeah, I don't know of many C++ developers who don't like the details, and Eric can attest to this. You know, there's so many different ways to optimize your code, and nobody's going to have the same opinion.
Right.
So if you spend any time on the C++ aliases, it's fun at Microsoft to see some of the debates that happen. And you guys are well aware of this.
Right.
It's a super powerful tool, and it enables you to do all kinds of things. So thank you for coming on to C9 Going Native. And by the way, congratulations for the release of Photosynth on WP8.
Thank you.
That's pretty rock star.
No, it's great to see Photosynth on that.
Absolutely.
On that platform now.
And that's a C++ app as well.
It's
underneath.
It's underneath. All the image processing is done in C++.
Thus,
right.
It's on WP8. Right on.
Right. Yep.
Thank you so much, you guys.
Yeah. You're welcome. Yeah. Thanks for having us.
Sure.
Yeah, thanks.
Awesome. That was fun, man. I mean, it's always great to talk to C++ developers because, you know, Niners have asked us consistently, how are people actually using the language inside Microsoft? Right. Well, you just met a couple of guys in MSR. They're doing really hardcore image processing algorithms and stuff like that. I mean, that's why you would use C++. But, you know, what did you get from the talk?
Well, I always find it interesting asking people how they're handling their code, right? If there's legacy code, and it turns out that the library code base looks like it was 8-9 years. It's developed over time, and part of the challenges with any language, especially something like C++, is the tension between what you had to do in the past and what you can do in the present. And you saw that, you know, things like exceptions, that some consumers of your library aren't necessarily happy with exceptions, or they don't want. That's not one of their scenarios, so you can't use them.
Yeah.
So it's interesting. I like that, you know, just digging under that, you know, hey, we're real developers here as well, and we have a lot of the same problems that our customers and communities using as well.
Absolutely, and I really like the fact, you know, that they're using SIMD instructions when, you know, they have to really optimize their tightest inner loops, and you can do that in C++. We talk about that, how you have this beautiful abstraction, and you can get really, really way out with templates and classes and interfaces, all the big kind of stuff. But you can also really wind down really, really close to the metal, like SIMD, and really optimize your code. And that is the beauty of C++. It gives you this giant spectrum. You can be super high level if you want, super low level if you need to. So, you know, anyway, blah, blah, blah.
But
the exception story is interesting too. We had a long talk about that. I'm sure you saw it already since you're at the Destructor now.
Right. But obviously they probably use a profile profiler before they went in and started throwing SIMD instructions.
You got it.
Back in the day, maybe people jumped right in into assembly just because it's fun. But hopefully, folks are profiling and only spending time when they need to.
Cool, man. Well, always great to see you, Eric. And speaking of optimization,